Hello, everyone. In this video, I'm going to keep talking a little bit about categorical propositions. In particular, I'm going to be talking about the operations of conversion, obversion, and contraposition. So what these different sort of operations allow you to do is change a categorical proposition into something that it is logically equivalent to. And this allows you to eliminate the number of terms that you have in a syllogism. And then it also just shows how various forms of logical relationships hold between different kinds of propositions. Okay, so let me get the marker board out here. Okay. Now, let me give you a quick example here. So consider this categorical syllogism. All right, so suppose we had all P are non-M, some S are M, therefore some S are not P. Okay, so all P are M, some S are, sorry, all P are non-M, some S are M, therefore some S are not P. Okay, now, as it stands, this syllogism is actually invalid. And there's a couple of reasons why this is the case. So first of all, we have more than three terms. Okay, so we have P, we have non-M, we have S, and we have M. Okay, so this commits the fallacy of what's called the fallacy of four terms. A standard form categorical syllogism can only have three terms. Okay, now, and the reason why the fallacy of four terms is problematic is because we have two middle terms here. So we have M, which is, you know, the middle term in this, what's called the minor premise, and then we have non-M. Well, clearly M and non-M are different terms. They don't designate the same class of things, obviously. So non-M designates everything that is not an M, and M designates everything that is not a non-M. All right, so we have too many terms here. Now, so aside from having too many terms, neither M nor non-M are being distributed in these propositions. So here, since this is an A statement, you know, all P are non-M, the only thing that's being distributed here is P. Some S are M does not distribute anything. So neither S nor M are being distributed in this second premise either. Okay, now, but believe it or not, all P are non-M is actually logically equivalent to no PRM, right? So if we have no PRM, some S are M, therefore some S, oops, don't want that capitalized, some S are not P, this over here, okay? This syllogism is actually valid, okay? So this syllogism is invalid. It's got four terms, and you know, we've got two middle terms, neither one of which are being distributed. This syllogism is valid. The middle term is being distributed, whoops, the middle term is being distributed here because the E statement distributes both. P is being distributed in the conclusion, and P is being distributed here. We've got a negative premise and a negative conclusion. We don't have two negative premises. I'll be going over the rules of syllogisms in another video, but this syllogism doesn't break any rules. So this is a valid syllogism. Okay, so these two statements, whoops, doing that. These two statements are logically equivalent to each other. So all PR non-M is logically equivalent to no PRM, but which statement you use in the syllogism can actually make the difference between whether the syllogism is valid or invalid. Okay, so that is why we use operations like conversion, obversion, and contraposition. What these operations allow us to do sometimes is to reduce the number of terms. Okay, so here we have four terms, but since all PR non-M is logically equivalent to no PRM, we can reduce the number of terms from 4 to 3. In this case, we're using the operation of obversion. Okay, now, so without further ado, let's just go ahead and get into it. So where? Okay, so this is the same sheet that I uploaded the other day. Okay, so first we have conversion. All right, so conversion only works with E and I propositions. So the move, the inference from a standard form E statement to a standard form or to a converted E, and the move from a standard form I statement to a converted I statement, that's only valid with E and I. So converting an A statement is invalid, converting an O statement is also invalid. Okay, now when conversion has one step, all you do is switch the place of the subject term and the predicate term. Okay, so no SRP is logically equivalent to no PRS, and some SRP is logically equivalent to some PRS. So I mean, and this is intuitive. If it's true that none of the S's are included in the P class, it would be true that none of the P's are included in the S class. And if there's at least one S which is in the B class, if those two classes overlap, if there's at least one member of S which is also a member of P, it follows that there's also at least one member of P that is also a member of S. Okay, and this will make perfect sense once we get into Venn diagrams and things like that. Okay. Now, obversion works with all three of those kinds of statements. So obversion works with A, E, I, and O. So obversion with any standard form categorical proposition is always going to be valid, okay? Now, so obversion has two steps. So the first thing you want to do is change the quality of the statement. So if it's a universal, you're going to change the quantity. All right, so if it's all, change it to no, and if it's no, change it to all. And if it's particular, you're going to change the copula, okay? So if you have an A or an E statement, you're going to change the quantity of the statement. Why? Because the quality is already kind of embedded within the quantity. All right, so if it's all, change it to no. If it's no, change it to all. Now, and if it's a particular proposition, you're going to change the copula. If it's R, change it to R naught. If it's R naught, change it to R, okay? Now, and then the second thing you do is replace the predicate term with what's known as its term complement, okay? So the term complement denotes everything that is not denoted by the original term, okay? So if your original term is P, right, the predicate term, well, the term complement is everything that's not P, okay? Now, this is easy to do when you're using variables, right? So the term complement of P is just non-P. Now, but what takes some ingenuity is when you have actual like natural language terms here, okay? So let me give you an example. If I have something like all dogs are animals, okay? So here dogs and animals are both count nouns, okay? That can very easily be obverted to, whoops, forgot my own rules here, okay? No dogs are non-animals, all right? So if your terms are count nouns, you can just simply throw a non with a hyphen in front of that. Okay, so that's fairly easy. So we started with all dogs are animals. The first step, we changed the quantifier. So we change it from all to no, since the quality of the universal is determined by its quantity. Okay, and then our predicate term was animals. So since it's animals, we just throw a non with a hyphen in front of it. Okay, all right. Now, but what if I have something like this? What if I have, let's go with the no SRP here. Suppose I'm starting with no, no cakes are things that all right, no cakes are things that should taste like dirt. I don't know. I'm not feeling very creative. Okay, now, so once again, we're starting with no, so we change that to all. Okay, so all cakes are, now what would be a good sort of term complement here, right, for things that should taste like dirt. I mean, what if we did this? No cakes are things that are, or I'm sorry, all cakes are things that are non-things that should taste like dirt. Does that make any sense? Okay, so notice what the non is doing here. The non is not qualifying this entire descriptive phrase, right? So if your term is a descriptive phrase, that's why you can't just throw a non onto like the word things, right? So all cakes are non-things that should taste like dirt. Well, how can you say that a non-thing should taste like dirt? That doesn't make any sense at all, okay? Now, so if your predicate term is a descriptive phrase, you can't just throw a non onto the first part of it. Why? Because again, the non is only capturing things. It's not capturing this entire phrase, okay? Now, but since we have a should in here, what we can do is actually change this term into its term complement by putting some sort of negation within the description itself. Okay, so if we're starting with no cakes are things that should taste like dirt, we could very easily change that as a term complement to something like all cakes are things that should not taste like dirt. Okay, so with descriptive phrases, there are ways of embedding a different kind of quality within the descriptive phrase itself. Or, if I say something like this, no politicians are people are, wait a minute, I'll put it this way, are things who support anarchy, right? So that would be logically equivalent to all politicians are things who do not support anarchy. Or you could say something like this. If you don't want to say all politicians are things who support anarchy, you could even say all politicians are things who oppose anarchy, potentially. Okay? All right. So if your predicate term is a descriptive phrase, it does take a little bit of ingenuity to figure out an appropriate term complement here. Okay. Now, same with proper names. Okay. So if your original statement is something like, all philosophers are people identical to. Okay. Well, if your predicate term is a proper name, you got to use the identity relation, and then you would say something like, people not identical to, something like that. Okay. All right. Now, so all SRP by obversion is logically equivalent to no S or non-P. No SRP is logically equivalent to all S or non-P. Some SRP is logically equivalent to some S are not non-P. And then some S are not P is logically equivalent to some S are non-P. Okay, so notice here with the particulars, we're starting with R, copula, and we're changing it to R not. And if you start with R not, you're changing it to R. Okay. Okay. Now, and then the last operation here is contraposition. Okay, so once again, conversion is only valid for E statements and I statements. Obversion is valid with all four, A, E, I, and O statements. Contraposition is only valid with A statements and O statements, okay? So there are particular fallacies here. So if you convert an A statement or an O statement, that's known as fallacy of illicit conversion, right? Now, if you contraposit an E statement or an I statement, or contrapose, I guess we could say, contrapose an E statement or an I statement, that would be fallacy of illicit contraposition, okay? Now, so just like obversion, contraposition has two steps. So the first thing you do is you switch the places of the subject and predicate terms. So you're basically performing conversion first. Okay, and then you replace both the subject and predicate terms with their term complements. Okay, so all S are P would be logically equivalent to all non-P are non-S. So all S are P is logically equivalent to all non-P are non-S. Likewise, some S are not P. The O statement is logically equivalent to some non-P are not non-S. Okay. Now, I will say it's very rarely that you're going to want to have a statement like this in the course of actual argumentation. Why? Because that's incredibly wordy. So it's going to be more likely that in conversation you might end up with something like this. Whoops. And then you want to change it, back. You want to change it to like a standard form O statement here. Okay. Now, so to give you a couple of examples here, if I'm starting with all things that love whiskey are things that love bourbon. So all things that love whiskey are things that love bourbon. The contrapositive of that would be all things that do not love bourbon are things that do not love whiskey. Okay, so originally my subject term was things that love whiskey, my predicate term, things that love bourbon. All right, so you switch both of those. So all things, not thing, all things that do not love bourbon, the term complement of things that love bourbon would be things that do not love bourbon, are things that do not love whiskey. So I started with all S are P, and the contrapositive of that would be all non-P are non-S. Okay. Okay, and then if I'm starting out with like something, all or some firearms are things that require regulation. Right, hold on, because this, whoops, should be are not. So some firearms are things that are not things that require regulation, right? So some firearms are not things that require regulation. The contrapositive of that would be some things that do not require regulation are not non-firearms. So starting with some S are not P. So some firearms are not things that require regulation. And I'm ending with some things that do not require regulation. Some non-P are not non-firearms, are not non-S. Okay, so again, all things that love whiskey are things that love bourbon, all S are P. We would have all things that do not love bourbon, all non-P are things that do not love whiskey, non-S. Some S are not P, some firearms are not things that require regulation. If we contraposit that, it would be some things that do not require regulation, some non-P are not non-firearms, are not non-S. Okay, so once again, you should consider yourself lucky that we do not speak in contraposited categorical language on a daily basis, because this can get really confusing. Okay. All right. Now, the last thing I'm going to mention here in this shorter video, because we'll be switching to categorical syllogisms, is markings for Venn diagrams. Okay. Now, and make sure you get this because it can be incredibly confusing. Okay. Shading a region of a diagram means that the region is empty. Okay, so if you've got a region in a Venn diagram and it's shaded, it's common to think that it's like chock full of stuff. Oh, well, if it's shaded, that means it's full. No. If you shade the region of a diagram, that means that that region is empty. Okay, it doesn't mean that it's full. It means that it's empty. Okay, now an X in a region of a diagram means there is at least one member in that region. Okay, so if you shade a region of a diagram, it means that that region is empty. Okay, and if you place an X in a region of a diagram, it means there's at least one thing in that region. Okay, now, and how we mark universals is we shade. Since we're talking about all and no, you got to account for everything, or all the members of a given class with respect to A statements and E statements. Now, with particulars, since you're only talking about at least one, at least one S or whatever term you're talking about, that is why you put an X. So you would always shade for universal statements, and you always place an X for particular statements. Okay. Now, so let's start here with the universal, all S are P. Okay, so draw a little Venn. Nope, I don't need text. I need to draw. What am I doing here? Okay. Now, no. Why can't I get this to work? All right, where am I at? Can I just free draw? There we go. Okay. All right. There we go. Okay, so I've got a quadrant here, and I've got one circle that represents the S class, and then one circle that represents the P class. Okay, so this circle represents all the members of S. This circle represents all the members of P. Okay, now, so anything that is in this quadrant is going to be an S, but it's not going to be a P. So anything which is an S but not P is going to appear in this quadrant, quadrant number 1. Now, or region 1. Region 2, or quadrant 2, you can use region and quadrant interchangeably. Anything that appears in this region of the diagram is going to be both an S and a P. Why? This is the area where S and P overlap. Okay? Now, and then anything in this region, region 3, this is going to be a P, but not an S. So anything over here is an S, but not a P. Anything in region 2 is both S and P. And then anything in region 3 is a P, but not an S. Okay? Now, and given the meanings of the markings, okay, so since shading means that a quadrant is empty, okay, if we take the statement all S are P, all right, okay, so if this represents the S class and this represents the P class, okay, well, if all of the S's are P's, the only place that there can be S's that are P's is in this middle region right here, region 2, okay? So if it's true that all the S's are P's, if any S's exist, they're not going to be over here in quadrant 1, they're going to be over here, okay? But if it's true that all the S's are P's, then that means that this region is going to be empty, right? So to mark all S are P, you shade the region where there could be S's that are not P. So the only place where there can be any S's is here in region 2. Since that's the only place where there can be any S's, this means that if there are any S's at all, they're all going to be P's. So all S are P. Okay. Now, if we've got a universal negative, the E statement, no SRP, okay? Well, that means that these two classes are excluded from each other. So that means that any area where the two classes, S and P, right? Any area where the two classes overlap, there's not going to be any members in that area of overlap. These two classes don't intersect, okay? Now, but in the Venn diagram, the area where the two classes overlap is region 2 or quadrant 2. But if it's true that there is no overlap between the two classes, well, that means that this middle region of the diagram is going to be empty. Okay, so to mark no SRP, you would shade that area of overlap between those two quadrants. Okay, now the particular affirmative, get our circles here. So here we've got some SRP. Okay, so all that means is there's at least one S, which is a P. So that means that there's at least one member which is in the area of overlap between the two classes. So these two classes intersect, in other words. Okay, now, but the area, once again, of intersection between the two classes is in this middle quadrant right here. But if there's at least one S, which is a P, that means that there's at least one thing here in this quadrant. So there's at least one thing which is both an S and a P. Okay. All right, and then lastly, the particular negative. Some S are not P. Man, I really can't write today. Okay, so some S are not P, so there's at least one thing which is an S but doesn't overlap with the P class. Okay, well, the only area where there can be S's that are not P's is over here in quadrant 1. So to mark the O statement, we would just put an X right there. Okay. So once again, I'll just quickly redraw all of these. Okay. So for the A statement, all S are P. So for some class S and some class P, we would shade quadrant 1. So if there are any S's, they're going to be in this quadrant right here, quadrant 2. Okay, and I'll use my mouse instead of the touch screen here. Actually, that's worse. Okay. So with the E statement, these two classes do not overlap at all. Well, that means that the area of intersection between them is empty, right? And if that area of intersection is empty, we would shade the middle region, the overlap between those two classes, right? The I statement, okay? So this is saying there's at least one S which is a P, so we would put an X in the area of overlap. So that tells us there's at least one existing thing here, which is both an S and a P. And then the O is just the opposite. So there's at least one S which is not a P. Once again, the only area where that can be is over here. So there's at least one thing here which is an S, but since this X doesn't appear in any region where the two circles overlap, this is an S, but not a P. All right, so these are the 4 different markings for these different kinds of statements. Now, and then what we're going to do with categorical syllogisms then what we're going to do with categorical syllogisms is just add another circle for the middle term. Okay, so when you're just dealing with one categorical proposition, you've only got 2 terms, a subject term and a predicate term. When you're dealing with a categorical syllogism, you have 3 terms. Okay, you have what's called a minor term, a major term, and a middle term. So since syllogisms deal with 3 terms, that is why we need a 3rd circle in the Venn diagram. Okay, and we will start getting into that in the next couple of videos.